Hello everybody and welcome back to another video. In this video, I will be covering the concept of taking the derivative of a scalar and how it will output a vector. Now, of course, this cannot be an exact derivative, so we will define a different operation. However, it is essentially a derivative in three different dimensions. So first off, let's look at when this would be applicable in real life. So we know from physics that the force of a spring system is equal to negative a spring constant times the distance that it has traveled from its equilibrium point, which is labeled by x, which is also a vector. So let's say that you have a spring like this. This is its equilibrium point, and you push it this way, you displace it this way. The force is going to push you away from that displacement you just made. So that is why the negative sign is there. We also know that the integral of force of the spring dot the derivative, or dot dx, derivative in the x direction, these are both vectors, is equal to our negative potential energy of the spring, which is equal to 1/2 kx squared. So now, this should mean, since this is an integral, this should mean that the derivative of this should just be equal to our force. However, it does not work out like that, as potential energy is a scalar quantity because this x vector right here is squared. So that means that it will be a dot product, which will output a scalar. So how do we go from a scalar to a vector if it's so easy to go from a vector to a scalar? It is actually not as easy. However, we do have this function for it. So from this, we get the equation that the gradient, this upside down triangle of our potential energy, is equal to the negative force vector. And this does not need to be solely with springs. This is with many situations. This is the usual. So now, let's look at what this means. So what this is saying is the partial derivative of the potential energy in the x direction, comma, the partial derivative, this squiggly d is the partial derivative symbol of the potential energy in the y direction, comma, the partial derivative of potential energy in the z direction. Now, what is a partial derivative? Let's look at a graph in 3 dimensions, as that is where this force vector exists. So this is our y, this is our z, and this is our x. So our partial derivative in the x direction, you will be going along a plane moving in the x direction, a line going in the x direction. So you will be treating z and y as if they are scalars. Now for the y direction, you will do the same thing. You will be going across a line which is at a constant point in the x direction and a constant point in the z direction. And the same thing for z, you will be going along a constant point in the x direction and a constant point in the y direction. So that means that when you take a partial derivative, let's say you are taking the partial derivative of xy with respect to z, this is just a constant with respect to z since you are treating it as such, so this will output a 0. So now, let's use this in some real-world applications. So first off, I will write this equation, which is just a rearrangement of our others equations. So negative the gradient of u is equal to our force vector. So let's say that our potential energy is equal to x squared plus y z. Now find our force vector. So first off, we will take the partial derivative of this in the x direction. So the partial derivative of x squared plus y z over dx. So this x squared just becomes 2x, and this is just 0. So this is 2x plus 0. So our first term, our partial derivative of u with respect to x, will just be negative 2x, since we have this negative sign right here. So negative 2x is our first term. Then our partial derivative of x squared plus y z in the y direction is going to be equal to, this is 0, and then this is just, imagine this as saying 5 times y. You will just get 5 as your output for the derivative. So this is just z as our output, since z is our constant. So this is comma z, and then for our partial derivative in the z direction, that would be x squared plus y z over dz, where these are partial derivatives. So this term is once again 0, so this is 0. Also, sorry, I forgot to mention this is negative, because we have to define it as negative as stated over here. So this is 0 plus y times a derivative of z with respect to z, which is just 1. So this is y times 1, which is just y. And when we multiply that by negative, we get that is just negative y. So our equation for our force vector is negative 2x, comma, negative z, but that is in the y direction, and then comma, negative y, which is in our z direction. So if you move, you will get a different force for your z direction if you move along a certain point in your y direction. So this is our final answer. I hope you all enjoyed this video and learned a lot. This is a very interesting topic, and it gets a lot more in depth when you go into electricity and magnetism topics in physics, and this, you will see this for everything else in physics. This is one of the key functions of mathematics, and yeah. So I hope you learned a lot from this video, and thank you for watching.